Yeah, so hey, pre-warning you, I am recording this class, so that's the one that's going online tonight. Okay.
You want that homework assignment?
What?
You want that homework assignment, please?
Yes, please. Okay, alright. Here's what we're doing today. We're going to do a few notes over section 10.5 today. That's all we're going to do. We will be done early today if you take notes. If you take notes today, I will not give you an assignment today. So take notes. It's your reward for actually taking notes today. So it's your reward. So if you take notes, we will not have an assignment. That means you can't have computers out or anything like that. So computers should go away.
Everyone better take notes.
Alright. Okay, so, alright, here's our goal today. I want to do a quick review. As you guys are getting out notes here, I'll just put the outline on the board. I want to do a quick review of vocab terms. Vocabulary. We have a brand new term that I want to talk about today that I hinted at yesterday that we didn't get to it. I want to talk about what a tangent is. One more time, we've already had that word. I want to talk about point of tangency. Talk about, what that word means. Because again, these are free game for the test. These two words for sure. So tangent, point, and tangent. We're going to talk about common tangents. That one is the one that we really introduced for the first time yesterday. Common tangents. There was like 4 vocab words we discussed yesterday. We had external, internal. Then we could describe circles as internally or externally. That type of thing. And the new part today, we have a brand new vocab word today that I want to introduce before we get to the new stuff today, which is the word secant.
Wow.
That's what I want to discuss today. Brand new vocab word. Okay. All right. Now, last thing here. We are going to finish with a couple examples of homework today, where if everyone takes notes, we won't have any. So. But the goal today is to do a couple examples, 2 that were from yesterday, just real quick examples of it, in case you were gone. And then we have like 3 or 4 new ones today, which we're only going to solve 1 or 2 of them. I'm just going to show you pictures of things that I want you to see, and then we're going to go through it. Okay, questions, comments about our notes today, what we're doing. Perfect. All right, let's go through this stuff here. This should be pretty easy. Okay. Alright. Perfect. Okay. First example, let's talk about what a tangent is. Can somebody describe to me the word tangent?
A line that crosses only intersects a circle once.
Good. Line that intersects a circle once. At any spot, doesn't really matter where, but it only touches a circle once, like that. Again, the big thing is, you did say it correctly, it is a line. You can draw this line anywhere you like. It doesn't matter where, but it has to hit that circle at one particular spot. Okay? Now, if we have cursive letters, you can call it like line L. If they have multiple letters on the actual tangent line itself, let's call this A and B. You could call it that. You could call it line AB with 2 letters and then arrows above it. I don't really mind which notation you use as long as you use them correctly. But the blue line here, that's tangent. Today, the goal is to talk about, how to use it for homework, but also, the importance of it. That's really kind of something that we haven't really discussed here yet. We've talked about, different examples, but this line is incredibly important. I've tried to convey it today. And we'll talk about a couple of different careers that you could go into that would actually use that. Okay? All right. But this is kind of the main thing. Now, point A. Point A, this spot is special. It's the location right where that tangent line actually hits your circle. That spot is called the point of tangency. Okay, that, for some reason, this vocab word really gets people. The point of tangency is the actual location that actually hits the circle. It's that one spot. Now, what we talked about for theorem 1010, the theorem we did yesterday and Friday, was that when you draw a line from the radius, from the center of the circle, like the radius of the circle, out to that point of tangency, you have a perfect right angle there. It's perpendicular to that tangent line. Okay, and we can actually do the math. Questions at all about tangents, radii, all that good stuff? Okay, this is the part that we used yesterday a lot in those examples. We did radii and we did the tangent line, and we tried to talk about, Pythagorean Theorem and all that good stuff. Okay, we're good?
Yes.
All right. Common tangent, let's talk about that. Okay, let's talk about common tangent. Okay, common tangents. Anyone have the basic definition of it? Talked about it since, what, last Friday?
That intersects two circles.
Say it again?
A line that intersects two circles.
How many times can it intersect?
Once.
Once. So there's two types of common tangents. So there's 4 vocab words we discussed. Okay? Alright, so here's the example. Here's the first example. Okay, we have 2 circles, right? 2 circles. Number 1. We have a tangent that could hit both circles like this. And terrible drawing, but you guys get the idea. Hits the circles both like that. What type of tangent line is that called?
External.
Say it?
External.
It's external. Okay? It's an external tangent or exterior tangent, however you want to say it. That is an external tangent to both circles. Now, what we discussed yesterday is why do they call it external? That line does not cross the segment connecting the centers. That's why it's external. It's outside of those circles. Okay, it does not cross the interior line that connects centers. Now, the second drawing we had yesterday was same picture again. Again, it could be 2 circles, it could be 3. But an interior or internal tangent connects 2 circles, but it does cross that center line. That line is called an internal tangent. That's called an internal tangent line. The line itself. Because it does cross the center line. So if I were to actually have 2 dots connecting the center, and you draw a segment connecting them, that line does connect. Okay, do we understand the 2 different types?
Yes.
Okay, I want to make sure that you feel comfortable with that. Second one, or I should say the other words. This is the part that I think confuses people from previous years. That you can describe the lines as tangent, you can describe the circles as tangent as well. Circles can actually be tangent to each other. So, one of the examples would be like this. You have 2 circles, and they perfectly touch on the outside. Those circles are called externally tangent circles. They touch on the outsides. The example I think I used was like a printer, the wheels of a printer. I've also talked about in some of the other classes today is like, if you're going to draw like a cartoon character, I know it seems a little goofy, but if you draw a cartoon character, typically the characters, the eyes, they always have like one big, one small, and they always have them connected. The 2 lines are connected perfectly at the center, that's a tangent. You know,
The eyes are oval.
okay, yeah. But that's kind of idea. So that's externally tangent. Now, the second picture, internally tangent circles. 2 circles are internally tangent. I think the example I used the other day was a pocket watch. We talked about, I think somebody said today an olive. I think that was a pretty clever description of that picture. But the idea is that you have a circle inside of another one and they're perfectly touching the outside. That's called an internally tangent. Now, one of the examples I said yesterday in class was the spirograph. Okay? I want to show you that picture today so you can actually see what I'm talking about. That it was a plastic piece you put on a piece of paper that was like circular in shape. It had like teeth, so like a cog. You put another gear on it that was like a little plastic piece, and you put your pencil on it, and then you rotate it around the outside, and your pencil would spiral, and it would make a very intricate design depending on where you started and where you went. So I'll show you examples of what I'm talking about, like how it works. You can buy them at like Dollar General. Some people say they have them. Once they see the picture, they're like, oh yeah, I had one of those when I was a kid. Most people have them. They're probably at home. I'm going to see if Mr. Oberman has one. I still want to talk to him, but he might just bring in one. I'll go get one from Dollar General. But I'm going to show you a picture of it, how it works today, because I have a small clip of it. But yeah, so those are the major terms. Internally, externally tangent circles, and then the lines themselves can be called external or internal. Questions with common tangents. Okay, we'll come back to that whole spirograph thing. I'm going to show you the picture here in a minute, once we get to the pictures. Last word today. Last new word today, I should say, before we get to the examples. We have to talk about the secant. The secant line is a brand new line we haven't seen yet. This is one of the new words. It's in the next section. They don't introduce it now. I like to introduce it now so you can compare it to a tangent line. Okay? Alright, so this is a secant. Okay. this line is a secant line. Secants are lines that intersect a circle twice. Twice. It's not a tangent. Tangents only intersect a circle once, depending on how long you make it. No matter how long you make it, I should say. But secants hit it twice. It passes through it. One of the secondary definitions, other than, it's a line that intersects a circle twice, it contains a chord of the circle. That's a secondary definition. That there is an actual chord in the circle that is on that tangent line. Or on that secant line, I should say. Now, one of the examples I've been using all day was in archery. You shoot an arrow, it goes through a target, it goes through the front and back, you did a secant. You went right through the object, front and back. You went through it twice, right? One of the crazy examples I use, because I like to talk about this a lot, when a meteor enters the atmosphere, okay, it passes through the atmosphere. If it has enough velocity and mass, it'll keep going. You'll probably see like a shooting star, like it's kind of burning up in our atmosphere because of the friction base. It might pass through and just keep going out into space. If gravity, if it's light enough, it burns up enough of its mass and energy, gravity might actually capture it and bring it back to the Earth and will make an impact crater. But that's kind of one of those things, like, and I think the most famous version of a meteor actually passing through the atmosphere happened back in 2012 or 14. It was above Russia, where an asteroid from space came through, actually entered the atmosphere, becoming a meteor. That's what they redefined it as. But it traveled at such a rate, when it hit our atmosphere, it slowed to a crawl, but it had such a mass behind it that it basically set off a sonic boom in the atmosphere, like an explosion in the atmosphere, that they said was like 10 nuclear weapons going off at the time. The energy released actually blew out all the windows in the city that it was above, like all the windows shattered instantly. It knocked people off their feet and gave them instant concussions, and it leveled trees for about 100 miles in all directions. And it was just, it never even hit the ground. That was the worst part. It just went through the atmosphere like that. And just, and the rock itself, the asteroid, the meteor, they said it was about the size of a Volvo, like a car. That's how big it was. But it was entering at, 30,000 miles an hour. Well, when it hit the atmosphere, it slowed, and the only way that it would slow is if it released energy. So that was the impact and the actual explosion that occurred from it. Really kind of a cool concept. You can still see like a bunch of news articles about it, because they're still doing a lot of research, because it was kind of first in modern history to actually have like significant damage to like objects, but never actually make ground impact, which I thought was kind of interesting. But yeah, so that's kind of like my geeky version of secants. But tangents, on the other hand, are actually more important. Tangents, on the other hand, the idea of calculus, Calc 1, the study of tangents is like the whole purpose of what calculus is. It's tangents are rate of change. A profession that uses tangents a lot would be like a civil engineer. Civil engineers are people that work on roads and do public service, like types of constructions types of stuff. Where I think the most easiest example to explain to somebody what a civil engineer does is, let's say you're leaving Garner and you're going out past Casey's, you go past Ace Hardware, you're going on that weird windy road that goes north of town, right? That road had a sign that said 30 miles an hour, right? That's like the base for the curve. That's what a civil engineer does. That 30 mile an hour sign, or whatever it is, I don't even know what it is anymore. Is it 30? Okay, that sign is based on the tangent to the circle. It's based on the tangent to that curve. That number, that mythical number that the civil engineer came up with, is based on a number, like a default number for the size of a car that you're in. They say, I think they use like 2 tons, so like 4,000 pounds, something like that, as your car. So it's between an SUV and a car. And if it's traveling at that velocity, and it were to have, like, let's say a flat tire, you could still safely stay on the road. But if you're going faster than that, with that type of weight, that the inertia would actually carry you off the curve. So it'd be a danger to the person on the other lane. So that's what those tangents are. It's kind of a cool concept, like that level of engineering, because they have to look at the curve itself, look at where it started, where it ends, see what the actual path is, and then calculate what the trajectory of an object would be going straight off of it, and then kind of rate what the speed should be in a vehicle. It's got a lot of math behind it, but it's based on tangents. It's based on this simple picture. But yeah, tangents actually have there's a lot more, obviously, but I think civil engineer is kind of the easiest way to explain a profession that uses it. You get a ton of money for doing stuff like that. And it's not even that, I wouldn't say it's not difficult, but it's not a job that people would think about that would actually use it. So, all right, questions? Okay, let me show you a picture of that spirograph, that internally tangent circle, and then we'll get to some examples, like homework examples today. All right, so here we go. The goal is to show you some examples of homework to make sure that you understand how to do it before we get there. All right, so all right, here is the spirograph. This is the types of like imagery that they actually draw. So very cool, very symmetrical, very like very kind of cool patterns. People switch colors to make them like look pretty. But the actual object itself, what a spirograph looks like when you first pull it out of a box, it basically just looks like this. You just have a little plastic piece, it has a bunch of discs. These discs have a bunch of different dots where you can place your pencil. And what you do is you pick up the disc, you put it on the grid that they give you, which looks like this. This is kind of a blown up like mockery of it, where it's a circle where it has actual teeth that are on it, the actual like sprockets themselves. You actually have the circle, the plate that would sit in the middle. So these circles are internally tangent. And if you put your pencil here and you drag it around the outside, it'll follow the little spiral and it'll kind of like wobble as it goes because it's following that tangent staying on the circle itself. But it will make the path. So what you're actually watching is like a GIF of like the path it would take, and what they're actually drawing there, like this kind of showing a mockery of it. It's drawing this one. It's drawing this one right here, where it's kind of making that oval shaped pattern. And so if you were to like put it on different spots on that actual plate, you would actually get, the actual drawing that you see there, and you start at different points and put different colors in there. So it's kind of a cool concept. It's pretty easy. I remember playing with one when I was a kid, but I don't remember whatever I did with it. But yeah, there's a ton of math that's involved there because of the actual circles themselves. In fact, if you actually look at this Wikipedia article that I found about it, because I just typed in spirograph, there's a ton of like calculus that's involved in like the shape it makes and the curves it makes and how they're all related. It's based on tangents. These are rates of change and stuff. Really kind of cool concepts for just a simple kid's toy. There's a ton of math there. For a toy that you can buy at, Dollar General for a couple bucks. So, alright. Kind of a cool toy, but spirograph. Cool. Alright. Moving on. Alright, today, there's a couple pictures I'd like you to go through. We're not going to go through all of these. The goal today is just to show you examples of what the homework is going to eventually look like. I want to do a quick review of what we did yesterday for those who are gone. And then show you the new stuff today. I have like 3 or 4 pictures picked out today of the new stuff, which is based on Theorem 1011 today. That's because we did Theorem 1010 all yesterday, that we did like 3 or 4 examples of it. Today was to focus on 1011. But this is one that we did yesterday. It's a very, very similar looking picture. You have a radius to a circle. You have a tangent to a circle, and what we know is from Theorem 1010, that's the one we really looked at Friday and yesterday, was that this has to be a right angle, and then you could do the Pythagorean Theorem, right? That a squared plus b squared equals c squared. C is always the hypotenuse, it's always the wall across from 90. So knowing how to set this up, this is 7 squared plus x squared equals 11 squared. And then you can do the math, right? And how to solve this is 49, that's x squared. This is 121. You'd subtract this across, you get something like 72 or something like that, and you take the square root of it. Something like that. I don't even know if that's 72. I'm making that number up. It's got to be close. 121 minus 49, 72. That was close. Right. All right. So, square root of 72, and then the idea is that you take the square root of it, which will be in between 8 and 9. Okay, 8 is 64, 9 is 81, so it's between 8 and 9, some decimal. But that's this number here. We did what, 3 or 4 of those yesterday, so I don't really need to go through that all. So that was kind of the first one. We did some other ones where we threw in some missing parts in different places, but the problem was, it wasn't really the math that was involved, that was the hard part. getting to what the decimal is. It was this part. It was just the setup. Like, can you even get the formula written down correctly? Then you probably know where to go from there. So the second example, this one is the one I want you to write down. This one right here. This is the one that I think we finished with as of yesterday. It was something very, very similar to this. Where they gave me the tangent line to the circle, that's 20. They didn't even give me the radius, they didn't give me that at all. And they didn't give me the hypotenuse, they gave me like pieces of the hypotenuse. The 12 is from the 12 here is from here out to T, so let's call this like point P to T, and R to P is X. So they didn't give me the whole thing. So this is the one we finished with yesterday. This is one I definitely want to review, because this one had probably the most complicated math involved. It's not hard, it just took steps to get there. I think that was the best way to put it yesterday. It just took multiple steps to get done. Okay? Alright, to do the math, okay? You're gonna move this X to this location here. Okay. So we move the X, because that's a radius, you can kind of put it anywhere you want. And then you can do your Pythagorean Theorem, because this is still a right triangle. The radius still hits the tangent line at a 90. And then you can do the Pythagorean Theorem, because this is A, this is B, and this would have to be C, because it is the hypotenuse. It's across from the 90. The 90 is always right where the radius meets the tangent line. So this is x squared plus 20 squared equals, now, what is the hypotenuse though? 12 plus x, yeah. Or x plus 12. That is your hypotenuse. So you take all of x plus 12, that's the whole hypotenuse, and you square it. This is the part we did yesterday. And what we did is we kind of focused on, like, how do you actually do this problem, right? That you separate it, you actually do the math. We're going to do that right now. That's why I want you to write this down. I'll give you a little bit of time to get caught up, because I know some of you are like trying to draw and scramble to get this down. I just started this out, just make sure it doesn't turn on. Because if it like powers down, it just deletes all the file. Like, it doesn't even save it, so I usually stop in the middle. So if it loses it, fine, we got half the work today. Okay, now let's do the math here. So what does a power of 2 actually mean?
Times by itself.
Yeah, times by itself. There's 2 of them, right? That you'd actually have 2 of those. You actually have to FOIL it or multiply it, I think I heard. Okay, that you're gonna actually multiply those. The part up here, this is gonna be 20 times 20 is 400. Okay, so this is the part we're at, and this is what we're doing yesterday, that you actually write out 2 of them. Right, the x plus 12, x plus 12. That's what power 2 means, that there's 2 of them. That's how I got the 400, 20 times 20. Alright, so here, this is the part that was new. Some people have seen it, some people haven't. We called it FOIL yesterday. F-O-I-L, right? First, outer, and last. I just call it distribution. Like, there's no need to a fancy name for it. You're just going to distribute twice. You're going to take the first item, the x, times everything in the back. And then once you're done with that, then you'll take the 12 times everything in the back. That's just what you do. It's kind of the easiest way to go through these. Alright, so to go through the math here, and I'll try to keep these color-coded, so that way it kind of makes more sense when you see it. Alright, let's go to the first part here. What's x times x? X squared. Okay, good. X times 12. 12x. Alright, so there's the first 2 items. Okay, if we go to the back items, 12 times x again. 12x. And 12 times 12. 144. Okay, so there's the math. Now to actually solve, this is where you add and subtract things across to both sides. So if I bring like this x squared across, you're going to subtract it across. It'll cancel out the other x squared, right? Because you're going to subtract it off, so it's gone. And so now we're left with 400 equals 24x's plus 144. So because I have the 12x and 12x makes 24x's. Then we just solve it. Now it's just algebra 1, right? So you're going to subtract the 144 across, get 256. You'll divide by 24, and that's something I need somebody with a calculator. It's more than 10.
10.6.
10.6? Seriously? Alright, so it's more than 10. 24 times 10 is 240. So if you divide that over, it's 10.6. Alright, Right, and that's x. And so on this picture, this is 10.6, that's my radius, and then this is 10.6, because that's a radius as well. So that means this whole stick is 22.6. You add 10 and 12 together, 22. So, but that's so whatever the question was, maybe it asked for, R to S, boom, there it is. It was 10.6, repeating. Questions, comments about it? Okay, so that was all the problems we did yesterday, right? That was the last one we ended with. It was a little more challenging than any of the others. But today, our goal wasn't to do these, right? The goal today was to look at 10.11, right? That other theorem that we had from Friday, and to do some examples of it. Now, the problem with 10.11 is that it's super easy. Like I consider these kind of challenging. There is like an actual challenge to it to figure out how to set up. But 10.11, there's not. So we're going to just look at a couple pictures. We may not even solve a couple of these. I just want you to see them so you know, like, if you were to ever have to do these on your own, you know what to do. Okay, does that make sense? Because they're easy. They're like stupidly simple. So here we go. Anyone still need that though? That was good. Okay, let me erase it. All right, let's go through the math here. Okay, so next picture. And this is one I said it was. Okay, this is the first one. This is based on 10.11. 10.11 said that you had a circle, you had an exterior point, and you do tangents. That exterior point contains two tangents. And what it also said is that if that point contains two tangents to the circle, the two tangents are equal in length. That's what it said. So if we know that this stick is equal to that stick, what can I do with those two pieces?
Set them equal.
Set them equal, duh. 5x minus 9, set it equal to the x plus 7. Like, that's all you do. They should be the same stick. The example that I use for people, just like for a visual aid, it's an ice cream cone. Now, if it's a perfect like ice cream cone, the two walls are the same size. Okay? Or it's a straw, right? It's a straw where if you're seeing the three-dimensional straw come out at you, the straw walls are the same length. Like, it's not suddenly going to radically change the wall of the straw. So then you solve, you subtract the x across, add the 9. I think you end up having like this x turns out to be, what is that, 16 and 4, 4. So then you plug it back in, so each wall is 11. If I plug it back into the picture. Does that make sense for how I did it? Okay, that's easy. Like, it doesn't really require a lot of math. So you're thinking, okay, well, that's easy. So what would be hard about this stuff? It's not, right? But they could change the picture up. So the difference in pictures, this is a different one. Same style, but you have to kind of figure out how that theorem 10.11 applies, right? So 10.11 said you have an exterior point, you have lines going to the circle, these are tangent lines, because Q and R and S are all points of tangency. So what we know is that this stick is equal to that stick, okay? So I could set 3x minus 8 equal over here. And since this is an exterior point and that's a circle and you have tangents, what can you tell me about these two sticks? They're equal, so that means that is equal to that one. Even though they're going to two different circles, and the circles are different sizes, the tangent lines are still the same size, because they're coming from the same exterior point. Does that make sense now? I know that's really weird for people to figure out. Now, if you were to actually set those equal, I think your x turns out to be a 9. Fine, and then you plug the 9 back in, and each stick is 19 in length for the outsides. But again, just knowing that those two sticks can be equal to each other, some people just like assume it, but they are equal because of that theorem 10 and 10. Okay, anyone still need the two pictures? Burke, you good? Okay, anyone else need it? All right, let's go to the next one. Now this is the one, I'd actually like you to draw this one. This is the one that I actually want to solve today, instead of just saying it out loud. This one has a subtlety to it. There's two parts to this one. It says find x. So find x, and then also find the perimeter of the picture. So there's two questions that we have to do. Find x and find the question. After this picture, there's only one more picture today, and then we're done. Okay, so we have a circle, we have a bunch of exterior points. It's kind of making a triangle looking shape. First question we have to find is x. So anyone have an idea how to solve for x? X is down here, by the way.
Set 14 equal to 2x.
Okay, good. These two have to be equal. The reason why I know that, that's an exterior point. These are tangent lines going to the circle. So then that means those two sticks have to be equal because of theorem 1011. Right? So 2x has to equal 14, so you'd have to solve and your x is 7. So boom, we're done with that one. Boom, check that off the list. We're done with x. Okay?
May I have your attention, please? Jamie from Athletico is now ready for any juniors or seniors that need to see her.
Okay, so we solved, yes, we have x is 7. Now I have to find perimeter. Perimeter means what again?
All the sides added together.
All the sides added together. We have to add up all 3 walls of this triangle. It is a huge triangle. Well, we already know one of the walls. One of the walls is 27. So we're going to have to add 27 to the other 2 walls of that triangle to find a total. We have to find the other 2 walls. Well, this wall down on the bottom is pretty easy. We transfer the 14 down, this is 14. So what's the whole wall?
31.
31. It's 17 and 14. So that wall on the bottom is 31. Does everyone understand that? 14 transfers, 7 plus 14, 17 plus 14. The problem is, this wall isn't obvious.
24.
It is 24. But how do we find it?
You said
Say.
17, put that on the other side as well.
Okay, good.
And then you subtract 17 from it.
Yeah, 27 minus the 17 means this has to be 10, because that whole thing has to be 27. So then the 10 can hopscotch across to here, because those walls are equal, like we did with the 14. And now you can figure out this whole wall has to be 24. So you can add those together, and if you add, that's a 12, carry a 1, that's an 8. So it's 82 inches. So we found both parts. Okay, do we understand how the 2 work together with the theorems? Okay. All right, last picture of the day. Now I was thinking, okay, these are all easy. Like some people, like they look at it and like, okay, that's stupidly easy. Got it. But how do we use this stuff for maybe a more difficult type of problem? Like I was trying to think of problems that you would probably see in the future. Maybe not in this class, but later on. And I was thinking, okay, ACTs are coming up for some juniors. What's a problem that I've had from years past that people have most definitely asked me how to do it? They just didn't know. They had no idea. They just guessed an answer. They didn't know what to solve for. And it's this one problem that kept coming up. And I found one of these pictures in your book, and it's even in my other textbooks. And it's this. Let me show you the picture here. Here's the picture that I keep saying over and over and over that people keep asking about. This one. It literally mixes everything we've learned up till now, almost together. It mixes circles, it mixes tangents, it mixes radii, it mixes segments, it mixes quads, because there's 4 set of figures, it mixes Pythagorean Theorem into this. I can tell you right now, okay, the question that they always ask, like what they ask for on this one, is find the length of P to Q. That's the question. And no, it's not 10. So, they ask for P to Q. That's the question asked. Now, it's not a perfect rectangle. You can see it. Like one wall's 6, one wall's 4. So it's not a rectangle. So it's not going to be 10. Because some people like, well, or some people might not even know how I'm getting 10. This 4 can transfer to here because the clock idea. The 6 can transfer to here. People add these 2 together, and then they just try to transfer the number across. The other wall is not 10 because it's not a rectangle. You can't just transfer the numbers across. It's not perfectly shaped. You can see it's not. Okay, I know there's a couple right angles in there because of the stuff we're learning right now. That a tangent line, that's an external tangent to the radius. These are right angles. The problem is, these aren't.
Jared Shaw and
not.
Anthony Sherwood, come to the office, please. Jared Shaw and Anthony Sherwood.
So, what you have to do is you have to make it a rectangle to solve it. So what you have to do here is make a right angle right here. Make that a rectangle. So if that's a true rectangle, this 4 can transfer across over to here, and that makes this distance down here what? 2. And that makes that a rectangle and a right angle. Why it's important? Because now you have a triangle that you can solve for that x. a right triangle that you can solve. Because if that's a true rectangle, if I find x on this triangle, that right triangle using the Pythagorean Theorem, I can transfer the number across. That's what you have to do. So it's mixing kind of everything together. That triangle that I have there is a right triangle. I'm going to flip it over, so this is what we're looking at. We have the 2 sitting here. We have the 10 as the hypotenuse, that's the big wall, it's across from 90. And we don't have that wall, the x on the bottom. That's the picture I'm looking at. And it's doing the stuff we just did now, right? So 2 squared plus x squared equals the 10 squared. It's not a hard problem, but if you've never seen it before, you wouldn't even know how to set it up. So that's 4 plus x squared, that's equal to 100. Subtract that over, that's 96, and take the square root of it. What's the square root of 96?
Uh-huh.
No, it's not 10, it's really close though.
9.7.
Sure. 9.7, say it's 9.9. That's all right. I'd say 9.9, but 9.7, let's say. I'll go with it. Sounds fine. 797. Okay, you guys are really close. Okay, 797, so almost 9.8. Okay, but that's the idea. The ACT would actually have 4 answers: A, B, C, D. Probably E, none of the above, but maybe one of the options is 10, because I know people just guess, oh, it's 10. But it's 9.7. That will be probably one of the other answers, or 9.8 maybe. They have you round. But kind of, it's not a hard problem. It's just Pythagorean Theorem. We did this like 5-6 times the other day, plus a bunch of other times in the chapter. But knowing how to set it up, you had to mix multiple things together, but it wasn't a difficult problem. It was just different. You just haven't seen it before. But I thought it was interesting enough we had to talk about it, because it's something that I get every year. Somebody always asks me a problem that's very similar to that. Okay, questions? Perfect. Done for the day.